Assalamu alaikum everyone. Last time we discussed about the basic construction of synchronous generator, that the synchronous generator consists of a rotor and it also has the stator. So the key thing that we noticed were that the stator consists of three-phase windings, whereas the rotor was our electromagnet. And the important thing was that um, the principle is that we want to have a rotating magnetic field inside the stator. So we want to have a rotating magnetic field vector which rotates. So in the beginning we said we can either generate it using with either we can have this happen with permanent magnet and rotating the permanent magnet inside the stator. That will generate the rotating magnetic field and it will induce the three-phase voltage in the stator. And we said we can also do that by supplying DC current to electromagnet to a coil, basically making an electromagnet which will generate the magnetic field, and some prime mover will rotate the rotor and it will be a rotating magnetic field. Okay, so that was the basic instruction. So the question that we wanted to tackle in this we started in the last class, and we also want to continue on this, that how do we supply DC power to field windings. So just to maybe to clarify it more, we want to supply the DC power to rotating field windings. Okay, so that's the problem, that your field windings are rotating. Okay, so how do we supply the DC power to the rotating field windings? So one obvious solution is that you connect an external DC supply with slip ring mechanism. Okay, and the idea is that you essentially want to make an electromagnet with a coil. So we want to have an electromagnet, and USCO then we can supply a positive and negative, and it will have a one directional pointing magnetic field. Okay, so and we can then rotate using we can then rotate the electromagnet with any prime mover. So yeah, so the idea is that you need to connect these windings always to the positive and negative. You do not want to flip the sign, okay, which the commutator does, and we discussed in the last class as well, that the way to do it is you connect the slip rings, and the idea of the slip ring is that the terminals do not flip when the coil rotates 360 degree. It means whatever the direction of the magnetic field is, if it is pointing in this direction with respect to the rotor, then it will keep in this direction, so it will, as the rotor rotates, so the direction of the magnetic field will stay same with respect to rotor. It means it will not flip the sign as we go around the rotor. So that was the one technique, to have a external DC supply and brush mechanism. So that is called that's the one method. So you can straight away identify the problem with this is the brushes and the slip rings, which we have mentioned in the DC generators and DC motors as well. Okay, these require, wherever you have brushes, you are sliding continuously on the slip rings. It means the brushes will tear down with the time, and you need to replace those brushes continuously with certain frequency of the maintenance. Okay, so that's what that's done. That's practical for some machines, but not for those machines. We do not want interruption due to the maintenance. So in cases we need to look for another method to energize the the field windings of the generator. So in order to energize the rotor coil, which is the rotor electromagnet, we have one more technique beside slip ring and brushes. We have what we call the brushless exciter. So the idea behind the brushless exciter is that you have one more set of one more generator which is mounted on the same shaft that generates the AC voltage on the rotor, and that AC voltage is converted to the DC with the help of the rectifier, and the rectifier is also placed on the rotor, and which converts into the DC voltage, and the DC voltage is directly supplied to the rotor field windings. So in order to see the details, we will try to understand this from this diagram, that we have the rotor. So what does this diagram does is it separates the rotor, so what things are on the rotor, and it separates what things are on the rotor and what things are on the stator. So let's see what do we have. So on the stator you have a main field windings. Okay, so maybe I draw the parallel diagram, which is how the physically things will look like. So that will clear the more about the placement of this stuff. Okay, so we have a single shaft which is being rotated by any kind of a prime mover. So you have a prime mover connected. So here, so the prime mover can be steam turbine, it could be a hydro turbine or gas turbine or anything else. So again, reminder, we are talking about the generator, we are providing the mechanical power. Okay, so we have the stator, which is the main stator, which is this one. So this stator is the main stator, or in other words the main armature that generates the three-phase output voltage, which is what we want to generate. So that is, for example, that is placed over here. So this is the side view. This is how the machine will look like. So that is placed over here. Okay, you have a stator on the top, and you have the rotor in between. So this, for example, this is our rotor. So this is the in other words, this is a field winding. So this whole thing will be the rotor. I will be talking about the field winding. So the field winding for our main armature will be just an electromagnet, just a coil that will be placed under this stator जो हमने यहाँ पे draw किया है. So that will be somewhere over here. ठीक है. So now, and so observe one thing, that this is now mounted on the shaft, okay, which is drawn in the red. Okay, and you have an air gap between the blue and the pink, which is the air gap between the stator and the rotor. Okay, so uske baad then we come to this part. So this is your one generator, and how does it's working is same. Your electromagnet, which is in the pink, rotates because of the prime mover, and it will generate a three-phase voltage in the blue windings. Okay, and you have a one simple AC generator, which is which works on the same principle as we described in the simple as a simple rotating loop in this fixed magnetic field. It means that what you have here, this part is basically the stator, which is generating a constant magnetic field. Okay, so जैसे हमने इलेक्ट्रोमैग्नेट्स के अंदर डिस्कस किया था पहले इन द सिंपल AC rotating loop के अंदर. So you have an electromagnets which generates a unidirectional magnetic field. ठीक है, so it's a same stator. ठीक है, so now it's generating the field. This is the interesting part. So now this is stator which is now generating the field. ठीक है, and so just point out that this is stator which is generating the field, and now you have a loop. You have a, let me pick the color. So you have a rotating loop or another set of three-phase windings, which is nothing but three. So we discussed okay, we have a rotating loop. So you have another set of, so basically you have a three set of windings, so which will generate the AC voltage. ठीक है, and so that is mounted over here. ठीक है, and that is mounted to the same shaft which is to the red one, right? So उसके बाद then you have a one interesting part which is the rectifier. So what will happen is that this generator will generate an AC voltage, and the rectifier is also mounted on the same shaft. So you do not need slip rings or split rings. So remember, why do we needed the slip rings and split rings? Because we wanted to get the voltage out of the shaft. Okay, so that was the key. But still, when the goal is to supply something which is already present on the shaft, so you do not need slip rings. You can directly connect the wires to the DC rectifier, and the rectifier will give you the rectified voltage with these, and everything is on the rotor. Okay, so no extra no any wires coming from stator to rotor or rotor to stator. See, okay, there are no slip rings, there are no there are no split rings. Okay, so let me describe it again. So what happens is, so what is a brushless exciter is basically a simple AC generator. Okay, but the interesting part is that in this AC generator, the armature where the voltage is induced is on the rotor. Okay, so observe this thing. You have an exciter armature. It means where the voltage is induced. So now this is on the rotor, and the field winding that is on the stator. Okay, so the field winding is on the stator. So what will this do? This will generate a AC voltage, and that AC voltage will pass through the rectifier. You will have a DC voltage, and that DC voltage will be supplied to our main generator, which is the main synchronous generator, जिसमें से हमें voltage induce, जिसमें हमें voltage induce करना है. उसकी field winding को, as we discussed, it requires the DC voltage. So उसकी field winding will be supplied the DC voltage, and that will generate the main three-phase voltage in our main stator windings. Okay, so which is the main armature. So now notice the words. So you have an armature, main armature is on the stator, exciter armature is on the rotor. Okay, so armature is the coil where your voltages are induced. Okay, the main voltages are induced based on which generator are you talking about. So this is how the brushless exciter works. This is a very interesting piece of a technology. Okay, so let's move ahead. So second method is to supply the DC power from a special DC power source mounted directly on the shaft of the synchronous generator, which is the brushless exciter. So if you I'll just show you the few pictures. के if you see कि हमारे पास we have the main stator. So this is, no, I'm sorry, the main rotor, just the main electromagnet. So this is the this whole thing is the rotor. ठीक है. So this is जो यहाँ पे highlight किया हुआ है. So this part, this is the stator, this is the field winding of the main generator, and this is the exciter. ठीक है. So what when you see it physically, आपके पास जैसे मैंने कहा कि यहाँ पे there will be one stator part and यहाँ पे there will be another stator part. So this stator will generate the field for this one, and this generator will generate this stator will generate the electric power. Okay, so if you see this one, so this is your brushless exciter. Okay, so this is just the one, this part, but in color. Okay, so one thing that I wanted to point it here, that you can see the diodes and rectifiers here, which are basically rectifying the power and आगे उसको supply कर रहे हैं to the stator winding, to the rotor field winding of the main generator. Okay, so उसके बाद then so if you want to see in detail about how these things fit together, so I've shared this animation. I'll share this animation link into the description as well, and you can access it through the PDF of the slides as well. ठीक है. So roughly it looks like this one. आपके पास जैसे I draw the structures कि you have a main so you have a single shaft, उसके ऊपर you have a field windings which are this one, which are mounted, and then you have a main stator जिसके अंदर आपके पास voltages induce होते हैं, and then you have an exciter generator. So exciter generator के अंदर your stator generates the field, ठीक है, and it will generate. So then you have a so this is wrong. So rectifier is over here on this part on the rotor, and you have the rotor, which is the armature of the exciter generator that generates the voltage, and that is supplied to the diodes, which rectifies it and transfers it into the stator rotor of the main generator, which needs the DC current to energize the field. Okay, so this is a very interesting idea. So basically, so with this basic structure, you can, with the help of, if you have a very, so this is the field winding of your exciter. So if you vary the field winding, which is the very small current, which is over here, okay, which is if you vary the field winding, you will vary the magnetic field over here. So it will change the voltage induced in the exciter, and it means that the higher the field winding, the higher the voltage induced, the lower the field winding, the field current, the lower the exciter voltage generated. So it means that the higher the voltage in the exciter generator, it will have a higher current in the rotor, in the synchronous, in the rotor of the synchronous generator. Okay, it means it will generate more voltage in the stator. Okay, so in the stator voltage and stator currents, these are the main voltage in stator, and those are much higher in magnitude than these values. Okay, so because this is just a field current जो उसको supply कर रहा है. So it means that you can actually implement a closed loop control if you want to control how much voltage that you want, and so that closed loop control is basically called AVR, automatic voltage regulator. Okay, so this is a important device which is installed into the generators as well. Okay, so you can see the one application of the control, which is to control magnitudes of higher quantity by controlling the magnitudes of lower quantity, which is the field winding जो यहाँ पे हम control कर रहे हैं. So yeah, so and you are controlling a much larger current which are being supplied from the main stator. ठीक है. Okay, so there is a one problem in the brushless exciter जो we didn't discuss के if we have a brushless exciter, then this brushless exciter requires the input three-phase voltage, or at least a single phase voltage if you're just using a single phase and rectifying with the one diode. Okay, so this essentially needed DC current. Say, so it means you need to have an electric power to run the generator in the first place. Okay, so you see the dilemma here. The generator is generating the electric power. So for example, if you are working on a field where there is no electric power and you are solely relying on this generator, then from where you will supply this electric power? So that's a question. और सो इसको सॉल्व करने के लिए वन टेक्निक इज़ ऑब्वियस, जो हमने उसके अंदर भी डिस्कस की थी इन डीसी जनरेटर्स, कि यू रिलाई ऑन द रेजिडुअल फील्ड विच इज़ द जो आपके पास स्टार्टिंग के अंदर आपके रोटर के आपकी डिवाइस के अंदर होगी, एंड दैट विल जनरेट सम वोल्टेज. ठीक है, एंड देन यू कैन फीड दोज वोल्टेजेस ओवर हियर, ठीक है, to power up this machine, and then it will build up the voltages as we discussed into the shunt shunt generator. In the DC shunt generator is the same idea. Okay, so that's a one technique. But if you do not have the residual magnetic field, then we will add one more complexity into the device, and then the machine is called the brushless exciter with pilot generator. So one more complexity. So let's see what does it mean. It means that till this point we have the same thing जो हमने अभी discuss किया, कि we have the main generator, and then you have a diode rectifier, and then we have an exciter generator, which is again an AC generator, which has a field winding on the stator and the armature winding on the rotor. Okay, so now we have another set of a generator, ठीक है, another generator which is called the pilot exciter. ठीक है, so what's a pilot exciter is that you have the you have a rotor which is basically so I'm sorry, you have a permanent magnet which is mounted on the rotor. ठीक है, so remember आपके पास you have a mechanical power. Just to maybe remind you again that we have a mechanical power there, so most of the time we forget this. We do not have the electric power, but we do have the mechanical power. See, because this is where the generator is working. So this shaft is connected to some prime mover. Okay, some prime mover is moving it. So now you have a one permanent magnet that is mounted on the same shaft. Okay, so that permanent magnet, because of the prime mover, it will generate the rotating magnetic field, as we discussed the very basic idea in the case of an AC generator. I told you that you can also do that with the permanent magnet by having a north pole and south pole. It will have a magnetic field, and if you rotate this magnet, it will have you have a rotating magnetic field, and if you have a windings on the stator, it will generate the three-phase voltage. Okay, simple. So you have a permanent magnet, it will generate the three-phase winding, so which is now on the stator. Okay, so this is again the same idea as the synchronous generator. Okay, but so you have a field on the rotor. So only thing that's different from this synchronous generator is the field is being provided by the electromagnet here, but here the field is being provided by permanent magnet. Okay, which is the pilot exciter. Okay, so same thing. Okay, so it will generate three-phase set of the windings in the pilot exciter armature. So that will be rectified, and this rectifier is on the stator. That will be rectified into the DC, and that DC will be supplied to this exciter field which was required, and then the process goes on. This exciter field, which is now the DC, and this you have on the rotor you have a three-phase set of the windings which are rotating. It will generate the voltage, and that voltage will be rectified again by three-phase rectifier. Now this is on the rotor, and this will generate this will convert into the DC, and DC will be supplied to the main field winding, and then that will convert that will generate the main voltage in our main armature. Okay, so then we will have a AC power. Okay, so that is all because we wanted to remove the brushes from the system. Okay, so now there is no wire connection between the stator and the rotor, and even though when you do not have the electric power to start the machine, and assuming you have the mechanical power, of course you can assume that because you are working on the generator, you are operating the generator, so you just have to move the prime mover and it will run your generator. Okay, so that is called the brushless exciter with pilot generator. So in this case, no external electric power source will be required to run the generator, but in the previous case you need an electric power source to run the generator. Okay, so this diagram kind of summarizes what is on the brushless exciter. So you have the same shaft which passes through all the devices. Then first you have a permanent magnet generator, okay, which is the pilot generator. So this will generate the voltage on the exciter on the stator. ठीक है, so यहाँ पे stator की इसकी windings होंगी, that will generate the voltage. Then you will have a rectifier over here that will be supplied to this exciter voltage. Okay, so this part is on the stator, and then you have a rectifier assembly. Sorry, you have a exciter armature here, so which will generate the EMF, which is the AC voltage, and uske baad then you have a rectifier assembly that will convert that AC into the DC and supply the field of the main generator field windings, which are on the rotor, and then it will generate the main voltage on the stator. Okay, so that will be our main synchronous generator. Okay, so this is how your whole machine will look like. So let's now move towards the more towards the analysis and modeling of the synchronous generator. Okay, so we derived this expression that about which was the relationship between the speed of the rotation and the resultant electrical frequency. We said that the electrical frequency that will be generated into the stator windings will be equal to the mechanical speed of the rotating magnetic field, and mechanical speed times the number of poles divided by 120. So it was just a scaling factor. So it means in this equation, electrical frequency is in hertz, and Nm is the mechanical speed, which is in RPM, and P is the number of poles. So that will be our electrical frequency that will be generated. So for example, if we see in our country, so different countries generate electric power in different frequencies. So US generates the power in 60 hertz, and in Asia, in Pakistan and India, most of we generate the power in 50 hertz, with the frequency of the 50 hertz. So for example, we have a 4-pole synchronous machine. So it means that what should be so we want to generate the 50 hertz frequency here. So in order to have a 4-pole, so what should be our the rotating speed of our rotors in the synchronous generators will be so maybe let's calculate it. So for example, so you have a 4 poles, so let's see from the equation. So Fe is a 50 hertz times 120 divided by number of poles. So we have a 50 hertz times 120 divided by the number of poles, which is 1500 RPM. Okay, So it means that our rotors should rotate at 1500 rpm. It means that our turbine should be capable to rotate the synchronous generator till the 1500 rpm. So for example, if you reduce the number of poles to P is equal to 2, then your required speed will increase to the 3000 rpm. Okay, it will double. Okay, so that's a trade-off here, whether you want to increase the poles and you have a lower operating speed. Okay, so उसके बाद then we have what's the internal generated voltage in the synchronous generator case. So we derived this expression. So expression is not visible. I will write it again here. So so let me make you recall that in EM3, when we were discussing about the basics, we derived this expression. We said that the voltage induced in a simple rotating loop is basically E induced is phi max times omega times sine omega t, sine omega t, where phi was the flux in the machine and omega was the speed of the rotation. Okay, so the same formula is applicable here. So essentially you have the relative motion is still the same one. So in that case the field was fixed and rotor was rotating, but in our case now the rotor is so the coil where the voltage is induced, that is fixed. Okay, but you have a rotating magnetic field. Okay, the relative motion is still the same. It means that our voltage induced formula will be the same, which is which will be this term. Okay, so it will be so for any phase for any single phase, E induced will be phi omega sine omega t, and if this is a one loop in the winding. So if you have a n number of turns in a winding, in a single phase winding, okay, so nc number of turns, just to be consistent with the book, and so it means the voltage induced in a single phase will be nc phi omega sine omega t. Okay, so if we want to find out the peak voltage, which is the Emax, so that will be simply nc phi omega. Okay, so that's our peak voltage. So and generally in case of AC generators, the voltage is not specified in terms of a peak, it is specified in terms of the RMS voltage. Okay, so that is usually represented by EA, and that is written as EA will be equal to, so the RMS voltage, all the equations are not appearing, so it will be EA will be equal to NC, so the same term, NC phi omega divided by under root 2. Okay, so we know the relationship between the Vrms is equal to V peak divided by under root 2. So we just divided by under root 2. One thing here that your omega in this case is the rotating is the rotating speed of your rotating magnetic field. Okay, so that now depends upon the number of poles as well. Okay, so in that case, so if your omega if you have a p number of poles, so in this expression, so this omega is the rotation speed in radians per second for RMF. ठीक है, जो हमारे पास रोटर की रोटेटिंग मैग्नेटिक फील्ड है. ठीक है, so but if now we have a p number of poles, then we know कि हमारे पास in that case the p will be multiplied with the omega. If you are just taking the mechanical radians per second, so in that case EA will be equal to NC P phi omega divided by under root 2. Okay, so now this omega is just the radians per second speed of the so the mechanical speed, okay, the speed in radians per second, which is, but now the mechanical speed of the rotor, okay, only that. But here this omega, so we can also differentiate. So this is omega mechanical, okay, and this is omega RMF. Okay, so so you can as you know, we also generalize the expression in our course earlier as well, that doesn't matter what type of a machine that you are working on, most you'll have the internal generated voltage will be phi times omega. This expression will be true, but in this case k is equal to NCP divided by under root 2. Okay, and as we said, k will always depend upon the construction of the machine. So in that case, k is equal to NCP divided by under root 2. So this is our important equation for obtaining what voltage is induced in the machine. Okay, so given the mechanical speed, number of poles, flux in the machine, and number of turns in each winding. Okay, so also we know that since EA depends upon the flux and flux depends upon the field current, so it means if you have a magnetization curve, which is generally your magnetization curve between the IF that you supply and the flux that is being generated inside the machine. Okay, so that looks like that. Okay, so now that magnetization curve will directly translate into the EA. Okay, because EA depends upon the flux. EA depends upon the flux, which is K phi omega. So it means if flux follows this path, so with respect to IF, the EA will be basically the magnetization curve, but with the scaled version. Okay, so and that curve is called the magnetization curve, or in case of AC machines, this has a term which is has a one particular term that is used, which is called the OCC, or open circuit curve. Okay, so that's just a term that is used. We have already seen this curve, but just a reminder, that behavior is still there in case of AC machine. I guess we'll stop here today, and in the next class we'll pick it from here, and we'll start modeling more components of the synchronous generator till we get the equivalent circuit, and then we'll work on the practice problem. I'll work on the problem, and then we'll see how all these equations are applied. Thank you very much for listening. Allah Hafiz.